So let's continue our lecture. The next chapter is about safety concept in engineering. Okay, to getting started, there's an exercise, a group work. The question is, are we able to avoid disasters? Have a look on the lecture material that I've uploaded on our Moodle platform about the disaster of Bad Reichenhall. It was a collapse of an ice rink building at January 2nd in 2006. Research along sources and documents and answer the following questions. What causes have been detected? List these. How are the causes interrelated? Show the interactions between the different causes. Third, what kind of risk management has been adopted? Can you briefly describe the semi-probabilistic safety concept in your own words? Why failed this safety concept? What was the initial trigger of the disaster? What was the reason? Fifth, what should happen so that such a disaster never appears again? And last not least, why is it impossibly hard to very difficult to get 100% safety? You find the materials on our Moodle platform, chapter Technical Risk Management, and scroll down lecture material part 2. And also read the paper about risk in engineering. You also find this on our Moodle platform and the chapter Lecture Scriptum all in one, Risk Engineering. Here is it. Okay. Now, let's do our second case study, a steel girders on 2 pillars. It's about structural engineering. For example, you have such kind of roof. And the question is, which loads influence our roof? We know there are loads like own weight or extensions that impact our buildings. Snow, wind, and some kind of extra loads, maintenance work, explosions, submergence of ground, and so on. All these kinds of influences lay on our building here on our roof. From statics or engineering systems, you perhaps know that you can build the reality into a model. And that's what we will do about the loads. You've seen here the own weight, snow, wind, and representing the maintenance laws. Okay, now the first question is, how often do they influence? Always, often, sometimes or rarely, or never. For example, the weight, the own weight of the structure is always there. What about snow, wind, and the maintenance load? Answer this and put it in the spare room here. The second question is, how exact can you estimate them? Can you estimate it exact, roughly, or not at all? Of course, if you're not able to estimate a load, then you're doing wrong. Ask an engineer. No. So this is not useful to use. Not at all, does not exist. So decide between exact and roughly. For example, the weight again. The weight should be estimated and calculated exactly. The third question is, do they, the loads, occur simultaneously? What about the combination of the loads? Is it probably or probably not? So, of course, it's possible that you have both snow and wind. But how probably is it? So, answer the question about the probability that loads occur simultaneously. Now, short excursion, introduction to structural design. A very simple static system is like this, yeah? Made of wood. You find it in the Alps, for example, or anything in Tyrol or Bavaria. And you have a kind of a system like this. A beam that has two cantilever parts on the left hand and the right hand side, and a part between. Okay? And now, we can imagine different load situations. The weight of the wooden construction, filled by water in the middle, and sometimes people are sitting, for example here, on the corner. It's a single load on the corner of the structure. On the second line, you see the statical system. Here the weight is always and everywhere on the beam, from C to A, from A to B, and from B to D. The water maybe is there if it's filled, or it's not there if it's not filled. So the answer is, it's not always there. And it occurs only in the middle when it occurs. So the water load is between A and B. And last not least, one sits on the corner of the construction, possibly on point D or at any other place. So it's not always there, but it's everywhere possible. So there are certain points of interests. For example, on the bearing at point A or on point B. And this situation is typical that you don't have to do both A and B. It's A or B. Because if you calculate the system on point A, because of the symmetry, you have calculated it on point B. So, this is the first point of interest. Another is on the middle of the beam, M. Or the third point of interest is on the edge of the cantilever, D or C. For each point of interest, the load situation has to be put into the worst case situation. The worst case, see the next slide. Worst case situations. If your point of interest is A, here, then you have to put all the loads on these places where you have the worst case situation. So we start with the weight. You have no choice for the weight. It's everywhere. So it doesn't matter if your point of interest is A or anywhere else. The weight is always and everywhere. And remark, the weight between B and D is unloading the situation. But nevertheless, the weight has to be put everywhere. What about the water? Yes, it causes the worst case situation for point A. So put it in the middle. And the seat, the person is sitting on the edge or in the middle of the beam or anywhere else. You sit the person exactly to the worst case situation, so exactly on point of interest, and this is in our case A. The second point of interest is the middle of the beam, M. For example, the maximum bending momentum has to be calculated. So again, you have to put in the weight everywhere. They have no choice for the weight. The weight is always and everywhere. The water causes a worst case situation also for the middle of the beam, M. And you exactly put your single load, the seat, at M to produce, because the worst case situation. And third, the point of interest is D, the edge of the construction. For example, we want to know the maximum vertical deformation at this point D. Again, the weight is everywhere. You have to put it on the whole beam. What about the water? No. You have to calculate an empty situation without water, because it would be unloading the point D. If you press here down, point D comes up, not down. So water has not to be set in the middle. The worst case is introduced by no water. And last not least, again, put the person at exactly the point of interest. That causes, again, the worst case situation. So putting the load is depending on the point of interest. And here we have three different situations. The next step is engineering design. You have to calculate the force in the point A, for example, the bearing force Fa. And this calculated force has to be lower than the allowed maximum force. With this, you can prove safety. In the second case, you have the bending momentum in the middle of the beam. You have to calculate it in the situation that causes the worst case seen before. And again, your calculated value here, the momentum, has to be lower than the allowed maximum momentum to fulfill the safety condition again. In the third case, the maximum vertical deformation at the edge here should be fulfilled. You calculate the maximum deformation due to this loading situation, and again, it has to be lower than the allowed maximum. I summarize. It's all about the equilibrium, that the impact has to be lower than the resistance. But how to calculate the values of impact and resistance? All quantities are usually distributed according to probability, the well-known Gauss curve is. Also here our impact and also the resistance. We learned about the slides before. Out of the slides before, we know that the impact should be below the resistance, or in other words, the resistance should be higher than the impact. But of course there are situations where it fails, where the resistance is below the impact. And your job as a structural designer is to get the impact below the resistance with design values. In the first step, you have to determine the Gauss score, for example, the median value of the impact. Then you add some safety factors to go from the left to the right. And then you have a defined design impact value. You do the same with resistance. You determine the median, the middle value of the resistance. Then you calculate some safety into it, make it safer to go from right to left. And last not least, you have a design value for resistance. And your proof at the end is that your design values have to be compared. And again, the impact has to be lower than the resistance. If so, you proved safety. Impact below resistance, according to the design levels. The design level includes on both sides safety, on the side of the impact and on the side of the resistance. What are the safety factors? The design values includes a safety factor, gamma impact, multiplied with the characteristic value of the impact. On the other hand, the resistance design value includes safety by dividing the characteristic resistance value with the gamma R, the safety factor. For further details, see my paper Safety Concept in Engineering, an Introduction.